All right, two more last examples. And so the first one's the sum of 1 over n factorial. And our intuition here is that factorials are extremely fast, growing to infinity. And so that means that this series is going to converge. And now we have to find a way of justifying that using these tests. And so the nth term test here is not going to be helpful because, as we just said, the terms go to 0. And so that's never helpful in that case. The direct comparison test is going to be helpful. And that's because we can compare to something smaller than a factorial that still converges. And so it's often the case that if you only have one term in the numerator or denominator, the direct comparison test will be helpful. The limit comparison test, for sort of the opposite reason, is not going to be helpful here, and that's because the leading terms are the only things here anyway. And so the limit comparison test often helps you pull out the leading terms from an expression, but we already pulled them out here. And the integral test here, again, not going to be helpful, and that's because 1 over x factorial as a function just doesn't make sense. And so we're not going to be able to integrate this to begin with. Okay, so now we can try and use this direct comparison test to see what happens. And so I know that 0 is less than or equal to 1 over n factorial. And now I have to find something bigger than this that still converges. And so it might help to write out again what n factorial means, which is n times n minus 1 times n minus 2 down to 3 times 2 times 1. And I know that I just need to show that this is less than or equal to something like 1 over n squared. Well, that would be easy if I just got rid of all of these terms in the denominator. And those were only making things smaller anyway. And so then I can say that this is just less than or equal to 1 over n times n minus 1. So that's equal to 1 over n squared minus n. And now I have to find some way of showing that this converges. And so there's really two options here. One of them would be to use the limit comparison test to show that this is just like 1 over n squared now, and we already know that that converges. A slicker way would be to use the direct comparison test. It'll just take a little bit less work. And I can replace the n with an n squared over 2, just because n squared over 2 is bigger than n. And so if I subtract this from the denominator, then I'm also making the entire expression bigger. And so that's a little bit slick, and so maybe you wouldn't see that right away. That's fine. Any way that you do to show that this series right here converges is going to be fine. But this would end up being equal to 2 over n squared. And then we know that the sum of 2 over n squared converges by the p-test, because p is equal to 2 in this case. And so that implies that 1 over n factorial converges by direct comparison. Okay, the last one I want to look at is this e to the 6n over e to the 6n plus 4 raised to the 6th. And so here the important thing is that this power right here is bigger, and the denominator is filled with exponentials, and so it's filled with bigger exponentials. And so this is exponentially tending to 0, because the bottom exponentials dominate over the top ones. And so it should converge. And now we have to figure out how to show that. And so the nth term test is not going to be helpful again because the terms go to 0. The direct comparison test in this case will be helpful, and that's because we have this plus sign right here, which is only making the denominator bigger. And so if we got rid of it, then we would end up with a bigger fraction overall. And so yes, and that's because we can eliminate the plus in the denominator. The limit comparison test would actually also be helpful in this case because we could pull out the leading terms, which would be the e to the 6n in the top, and then in the bottom we'd have an e to the 6n raised to the 6th. And so that would give me an e to the 36n. And so these are the leading terms. And in this case, finally, which is really the reason why I had this example, the integral test would be helpful here as well. And that's because e to the 6x divided by e to the 6x plus 4 raised to the 6th can be integrated. And also, this is a positive, continuous, decreasing function. And the reason that this can be integrated is because you could do a u substitution with u is equal to e to the 6x plus 4, and that du would cancel nicely with the e to the 6x in the numerator. And so this would be an easy integral to compute. And so that's the sort of thing that we're looking out for the integral test is there some sort of chain rule going on or a u substitution that would make it look nice? And in the example problems for this lecture, you will find an example where you do want to use the chain rule and a u substitution in order to analyze whether or not it converges. Okay, so maybe it's easiest in this case to just use the direct comparison test. And so in this case, we have that 0 is less than or equal to e to the 6n over e to the 6n plus 4 to the 6th. And then, like I said, this plus 4 is only making the denominator bigger, and so it's making the entire thing smaller, and so I could just get rid of that. And I know that this is less than or equal to e to the 6n over e to the 6n to the 6th. And so that's e to the 6n over e to the 36n. And then if I simplify that using power rules once more, then I have that this is really 1 over e to the 30n. And if I write that sum, 1 over e to the 30n, I could rewrite it as 1 over e to the 30 all raised to the n. And so that converges because it's geometric. Again, I want to specify what r is here, and that's 1 over e to the 30, which is less than 1. And so that means that the original series, e to the 6n over e to the 6n plus 4 to the 6th, converges by direct comparison. But you could have used the limit comparison test or the integral test, and they would have told you the same thing at the end of the day.